Welcome to our first mathematics episode. Today we're talking about linear regression, which is a mathematical technique to model linear relationships between two or more variables. If we've got two variables, we're talking about simple linear regression, otherwise it's called multiple linear regressions. We've got two main applications. The first one is the prediction of data, if we've got observed values. For example, you could predict the duration of a hospital stay in proportion to someone's age. On average, older people will stay in hospital for longer than younger people. The second application is to explain the proportion of variation that can be explained by the variable of interest. So, for example, if someone does a lot of sports, he or she will have a lower BMI on average than someone who doesn't do sports at all. So we can use linear regression to plot a dependent or outcome variable, so in our case the BMI, against an independent or predictor variable, in our case the time someone spends doing sports. There are also more complex models where you incorporate more than one variable, which is done, for example, in medical research. And yes, so that's a common way of applicating linear regression. The formula is depicted here, where k is for the slope of the relationship, x is the value that you need to calculate z, and c is the intercept, so the point where the graph connects to the y-axis. To perform a linear regression, you've got to check for 4 assumptions that have to be fulfilled. The first one is pretty obvious. The dependent and the independent variable must have a linear relationship between them. This means that when x changes, y changes as well. Then, for the second assumption, there's a complex word called homoscedasticity. And here you can see what this means. So that means that there's a random pattern for the data points. If you take a look at the second and the third picture here, you can see that there is kind of a shape, and that's not what we want, because the variation around the regression line has to be approximately the same for the lowest and for the highest values. The third assumption is that the data points follow approximately a normal distribution around the regression line. That means that the vast majority of data points is close to the regression line and that fewer data points are further away. The fourth assumption sounds complicated, but is actually not that complicated when you have an example, and I will give you one. So, it says that the deviation from the regression line for every data point has to be independent of every other data point. And this is the case, for example, when you have multiple study centers. Think about a medical when you want to test a new drug and you've got a clinical study which you perform in various study centers. It's possible that in these centers they measure, let's say the cholesterol level with a different technique, and therefore you get differences which are not because the drug lowers cholesterol, for example, efficiently, but because the technique of measuring cholesterol is different. So, then we've got the two main goals which are relevant for fitting a line, and the first one is that the distance between the mean outcome line and the regression line has to be minimized, and the second is that the distance between the regression line and the data point, which is also called residual, has to be minimized as well. To find this best fitting line, which explains most of the variance, the method of least squares is used. So you basically just take the residuals, the distance from the data point to the regression line, and you take the square of that, and then you try to minimize this value. This is of course done by computers. This is not done by hand. This would be way too complicated. A way to measure the strength of a model is the so-called coefficient R, which is calculated by the sum of squares for the regression and the total variance and r equals 0 means that there's no linear relationship, whereas r1 means that the linear relationship is perfect and that the independent variable explains 100% of the variation of the dependent variable. This is, of course, hardly ever the case in nature. I guess it's never the case. And you can use a t-test, for example, to test if the model is statistically significant. Thanks for watching. Maybe you want to take a closer look at the drawings, and this might be easier to understand it. And I hope you liked it. See you in the next one.